Okay, any questions at all about the class, about, I guess, the PhD program, about just anything in general?
For the homework, like you mentioned in class, there can be multiple kind of FFT solutions to your PDE, right? And like the only way you can kind of evaluate whether or not they're same is by taking the infinite sum, like by plotting it. Is there like a specific form, like on the homework or on exams, that you want them to be in? I don't know if that's
Can you
correct.
give me more context for your
Um,
question? What do you
like
mean there can be multiple solutions, stuff like that?
So, like on October 16th, we mentioned that we could use either like a shift function saying it's f of yt is equal to 1 minus y minus the infinite sum of blah, blah, blah,
Right, right.
or 1 minus e to the n pi squared t times sine n pi y.
Yeah, I'm sharing right. It's right here what we're talking about, right?
Yeah.
Yeah.
So, like, for example, like on the homework, um, if we say like non-dimensionalize our solution or our PDE or like apply some different transformation or just like use a different approach but get like a valid answer like
Then that's perfectly fine, as long as it works out, and it is physically meaningful and all of that stuff. I think the way that the homework problems, or at least many of the homework problems, are worded, it actually asks you to evaluate like a known quantity, not a known quantity, but like, how much flow happens before the fluid comes to rest. Um, or like what's the flow rate, or it asks you to actually plot things and stuff like that. And so in cases like that, for instance, it doesn't really matter what your actual sum looks like, because if the sum is wrong, then you won't get the same plot or the same result. Um,
okay.
uh, in this particular case where you're mentioning where there are two ways of doing the problem, yeah, that's totally right. And you can, if the problem is worded ambiguously, then you can pick either one. I think what you might be thinking about in the homework is, though, sometimes the homework actually asks you to like solve it in a certain way or something like that, in which case, solve it that way.
Okay.
As an example, I think problem 4 asks you a variation of the example that I'm about to show momentarily, um, and asks you to solve it in the alternate way of what I'm going to do in class. So,
Okay, yeah, because like I was trying to, or I mean, I guess this is a question for office hours. I was just trying to non-dimensionalize number one, and then like I ended up getting a different answer than if I were to like just leave it as it were.
okay, sounds like an office hours question. Yeah. Yeah.
All right.
Okay.
Thank you.
Speaking of office hours and such, I'm gonna, homework 5 material ends at the end of this lecture, and that also is the end of exam 1's materials. Um, I don't know if you're gonna get back your homework, although I don't really know what getting back your homework means nowadays anyway, but you'll definitely see the solutions for homework 5 before the exam. Um, I normally do one more example for FFT, but I'm not going to get to it during normal class time. And so during this week's office hours on Wednesday after class, I will cover that example in case any of you guys wanted to stick around and see it. I'll try and record it and stuff like that as well. Just one more example to try to show you other variations of how the solution method can go. Based on your responses, not everyone responded to the poll, but for those of you that did, thank you. For those of you that didn't, I'm assuming it just any time is okay for the exam. I mean, based on your responses, we're gonna go with Thursday, October 29th at 6 to 9 p.m. I know that there's not a time where everyone can make it. If that's actually a time where you actually can't make it, contact me and we can either do I'll chat with you. Maybe we can do like a makeup or something like that. Okay, that's pretty under normal circumstances. We would often do makeup times anyway. Okay. As a result, next week we don't have a homework due, and so that implies that the week's office hours are going to be basically exam review. So Monday night, Zhao will probably do a review session, and then Tuesday during his normal office hours, he'll have just questions and stuff like that. And I will do the same during my Wednesday office hours. Okay. And then the exam will just be held over Zoom, basically, and I'll give you guys some more feedback about the actual format and stuff like that once things come a little bit closer. Okay, any questions? All right, then let's go ahead and continue with what we were talking about. So we've just been doing a lot of FFT as we mentioned. So I will naturally need to go back and review some things that we did. For example, on Friday, we talked about the more general FFT solution in the general PDE like this, that looks like this, where we have some sort of second order differential operator. Then, as long as this operator is of a form that looks something like this, which is often the case, for instance, in the problems that we've been doing so far, it actually does follow this form where the function p of x equal to 1, q of x equal to 0, and w of x is equal to 1, then you can do FFT on it, because this then gives results in basis functions that are orthogonal and have an inner product like this. And then you can do all the different steps of you can figure out what the base functions are and then do all the steps of the FFT. Today we're going to do an example of that. And so I'm just going to show, I'm going to go ahead and sketch out what we're doing here. Okay, so I'll say, let's see, we'll consider vertical pipe fluid, where the bottom suddenly falls out. Okay. This vertical pipe is going to look something like this. Let's not worry about, we can say that it extends infinitely up and down or something like that. And so we're not going to worry about end effects at all. It's a natural avenue to talk about cylindrical coordinates, right? And so we're going to have an r direction like that, and then we'll let our z direction extend that way, which then means that we also have a gravitational field going down like that, g, okay, and we'll say that our pipe has dimensions or has a radius of r like that. Okay, and so you can do all the stuff that we would normally do to simplify the Navier-Stokes equation. If we do that, let's just go ahead and zoom directly to the z component of the Navier-Stokes equation. You get something that looks like this. Where g here is positive because this g is in the plus z direction, right? It's like this g can be something like 9.8 meters per second squared times ez because it's going in the positive z direction, right? And then of course we can also just slightly simplify this by using the kinematic viscosity. Okay. As we've done in the past, we can also non-dimensionalize this equation, so let's do that. And okay. Sorry, non-dimensionalize. I don't know why that dot isn't going away. Okay, so we'll have an r squiggly, that's going to be r divided by r here. Our non-dimensional time is going to be the same as before. Our length squared over kinematic viscosity. And then our non-dimensional velocity, in this case, we actually don't know, right? There's no velocity given in the problem. But for now, let's just call it u, and then we'll figure out what that natural velocity scale is going to look like. Okay. So if we plug these into our equation here, into our equation to get something non-dimensional, then dv z dt looks something like this. it's unclear how that works, then you basically note that dvz dt should have units of velocity over time. So again, the complicated way of doing this is we can apply the chain rule. Basically, we do dvz dt is equal to something like, df dt times dvz df, and then calculate dvz df, and you'll find that you get a term of u at the beginning. The simpler way of doing this is to basically take this term and then realize that it has units of velocity over time. And so on the top, we need 1 unit of velocity. That comes from our u right here. And then we need 1 unit of time on the bottom, which is r squared over nu on the bottom here. And then, of course, multiplied by our non-dimensional quantity. Same idea on the right-hand side. G doesn't have any variables, so it just stays that way. And then this other term looks something like this. Sorry, not dvz, df, dr, like that. And again, this term on the right-hand side, you can do the chain rule. It gets a little complicated because you have so many like layered sort of things, but it all works out basically the same. Or you can realize, you can go through and do a little bit of bookkeeping to realize that this derivative right here has to have units of velocity per length squared. For instance, this derivative is velocity per length times length, so just velocity, one more derivative, velocity per length, and then divided by r, giving you velocity per length squared. And so out in front, I have a velocity per length squared. And then, of course, we can't forget about our kinematic viscosity. Okay. So if that's the case, then it makes sense that perhaps a correct scale for a velocity here might look something like this. Okay. So if we, again, this doesn't really matter, but if we were to select our u here, if we were to set our u here to be equal to gr squared over nu, then it just makes the math work out really well. It allows us to cancel out some things and turns our PDE into this. And then, of course, our final solution is going to look like something, 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 but then it's going to be multiplied by gr squared over nu, or it can be multiplied by u, but again, u is just equal to gr squared over nu. Okay. And just like before, I'm going to eliminate all the squigglies because I'm going to get tired of writing all the squigglies. Basically, every time moving forward, I write an r or a t, just imagine that there's a squiggly over it. All right. So just like before, we also need to have boundary conditions here. And so we have one derivative in time, and we have two derivatives in r. And so therefore, we need three boundary conditions, one in time and two in r, right? So our boundary condition in time, we often call the initial condition. We have a vertical pipe of fluid that's just sort of sitting statically. So the initial condition might be that f is equal to 0 at time t equals 0. Okay. And then we have two boundary conditions. These are the same boundary conditions that you would get under normal pipe flow, which we already covered a couple weeks ago, right? You have a no-slip boundary condition at the surface or at the wall. So f is equal to 0 at r equals 1. And then you have something like a no stress condition, or you can also call it a symmetry condition, or you can say a finite condition, r equals 0. So just f remains finite at r equals 0, or you can say df dr is equal to 0, etc. Right? This is exactly what you would do in a normal pipe flow fluid problem, right? And so now it's just a matter of doing our FFT solution. So let's do that. Okay, remember it has 4 steps. Number 1 is basically express in terms of basis functions. Basis functions. Okay, here we don't know what the basis functions actually are. And so our step 1 is going to be a little bit more complicated than what we've seen in the past, right? In the past, what we've done is basically say, well, we can go ahead and write that here. F of RT is going to be equal to some sum over basis functions. Okay, but the question now is basically what is that, right? To remind you, in the past, we had something like that, right? But that's not true here. Okay, and so now to get this, to remind you, the way that we solve this problem, if I can, there we go, yeah. Or the way that we found the basis functions was we solved this differential equation. Sorry. Right? And to remind you, the reason why we did that is because we needed to satisfy all the different, we need to make the integration by parts work and stuff like that. Okay, and so here we're gonna have to do something similar, right? So here, we must solve this differential equation. Okay, where L of R is equal to 1 over R d by dr times R d by dr, like that. Okay. Just to draw a quick analogy, we've talked about this more general case of equations. These were called Sturm-Liouville problems, right? As we opened at the beginning of class by reviewing what we were doing on Friday, this was the general form of that second order operator, like that. And perhaps you can see then, compared to what you just wrote down, and I'll try and scroll down so you can do another quick comparison. Compared to this, then we basically have this form of the equation, but with special cases of P, Q, and R. Just like how before our P was equal to 1, Q is equal to 0, and W is equal to 1. Now our P is equal to R, X, R, same thing, right? Our Q is equal to 0, and our W is equal to R, right? So what I'll say is, this is a Sturm-Liouville problem. With P of R is equal to R, Q of R is equal to 0, and W of R is equal to R. Okay, so basically, we need to solve an equation that looks like this. And I can rewrite this equation. Let me go ahead and multiply some stuff out. Here, I'll go ahead and product rule out the left-hand side over here. 1 over R of, oh, sorry, this is 1 over R of d squared phi dr. Sorry, there's not that in front. Plus that. And commonly for these sorts of equations, we like to pull everything to one side. My OneNote is frozen, sorry. There we go, okay. Okay, with two boundary conditions is that, remember, the boundary conditions have to be the same type as what we have in our initial problem here. And so the two boundary conditions are that phi is equal to 0, at r is equal to 1, and that d phi dr is equal to 0, at r is equal to 0. Okay. Does anyone know what the solutions to this equation are?
They're Bessel functions.
They're called Bessel functions. Okay. The analogy is maybe pretty similar. We've done a problem that looks like this. Remember, the solutions were sines and cosines, right? Does it sound familiar? This is how we were. So when we solve this equation, we end up getting sines and cosines here. Okay. For an equation that looks like this, it's a little bit more complicated. They're called Bessel functions. Okay. I'm going to open up something in just a second to show you guys what they actually are. But the general solution in this case looks like this. Okay, what is J0 and Y0, you might ask? It's a special function, just like, but you know, if you were to think about it, if you came from a different planet and had no idea what a triangle was, or a circle or stuff like that, and you asked what are sines and cosines, and I would have said the same thing. It's a special function with special properties. Okay. In this case, we're talking about Bessel functions. So Bessel functions are defined as, sorry, I'm going to share something new. Are actually defined as differential equations, or as solutions to differential equations that look something like this. Okay, you can see how this differential equation is essentially the same as just what I wrote down, except without this sort of lambda thing, but you can apply the chain rule and get the lambda in there. Okay, I encourage you to read this article a little bit, but the solutions to this equation are what are called Bessel functions of the first kind, which are J, and Bessel functions of the second kind, Y. Okay, the general Bessel equation looks like this. The equation that we're dealing with in this class is when alpha is equal to 0, and so that's why we're talking about J0 and Y0. Okay, just so you guys know, this is what J looks like. Don't worry for a second about J1 and J2, the green and the blue ones. Just worry about this red one. That's what J0 looks a little bit like. Okay, you can see it looks a little bit like a cosine. Okay, kind of like how cosine of 0 is 1, J0 of 0 is also 1. Okay, and it also oscillates just like a cosine does. Okay, there's also Bessel functions called Y0, and that's what this red one is. Again, don't worry about J1 or don't worry about Y1 and Y2, the green and the blue. Okay, this looks a little bit like a sine, although unlike sine, which the value is 0 when let the sine of 0 is 0, here this actually goes down to negative infinity at 0. Okay. Again, it oscillates just like sine and cosine. One big difference between sine and cosine and the Bessel functions is that the Bessel functions actually asymptotically approach 0 as the argument goes all the way to infinity. Okay. Just like sines and cosines, as I mentioned, they oscillate, and so that means they also cross the x-axis at certain points. Okay. For sines and cosines, those crossing values are equal to things like n pi. That was how we were able to get our eigenvalues to say that, you know, lambda n is equal to n pi and stuff. And so we saw something like, that's why our basis functions were sine of n pi y, right? For Bessel functions, those crossing points are equally as important, but they are not as well defined. Okay, these are called the zeros of the Bessel function. They don't have any special values or something. You just have to look them up, and you can also find them in MATLAB. I think the function is just Bessel 0. Maybe there's a similar function in Mathematica as well. Okay, and so we'll get to that in just a second. But basically, those are Bessel functions. There are also some important properties that are going to be useful for what we're doing here. So I'll say a few important properties. The derivative of a Bessel function of J0, I'll say, like that, is equal to negative lambda J1. Sorry, I already wrote the J. Like that. Okay. And then the derivative of J1 with a special R in the middle here looks like J0. Okay. So just, I'm going to share the Bessel screen in just a second again. Okay. And you can also find these properties on the Wikipedia article. You'll have to page through a few other properties that maybe you guys care a little bit less about. Okay. But anyway, so these are important properties of the Bessel functions. One analogous way of thinking about this is if J0 can be thought of as a cosine, then J1 can be sort of thought of as a sine as well, because the derivative of cosine is equal to negative sine. Okay. And the derivative of sine is equal to cosine, kind of like what we're seeing here, although you have to worry a little bit about these different R's and stuff. Okay, and that's what makes Bessel functions a little special. Just to show you again, here was what a Bessel function looks like for the J0s and the J1s and stuff like that. This red line looks a little bit like a cosine, as I mentioned, right? This green line looks a little bit like a sine. Okay. And you can see how, for instance, like the minima and the maxima points of the red line are the points where the derivative of J0 is equal to 0. That's also where J1 is equal to 0, right? You can kind of see right here corresponds to this point, right here corresponds to this point, etc. Okay. Those properties, as I mentioned, that I mentioned earlier, actually apply directly to y's as well. Okay, so the derivative of y0 is also equal to y1 with some special r's in and stuff like that. Okay. And so we're going to need to use that in just a second. So I'll say these also apply to y Bessel functions. Okay. So given our knowledge of this now, we can find the basis functions. Okay. Again, these are the basis functions that we're going to need to figure out our FFT solution. Okay. And we'll do this using the boundary conditions. Okay. So let's actually use our second boundary condition here. Our second boundary condition is that the derivative the derivative of phi is equal to 0 at r equals 0, or we can just say that phi is finite at r equals 0. Okay. If we know that our general solution is this, a times j0 plus b times y0, then let me switch again to that other screen here. This is what y0 looks like in red. And what j0 looks like in red is like this. Only one of these is actually finite at r is equal to 0. Okay, and so we know that the term in front of that has to be equal to 0. Okay, so what we had before was that phi is equal to a times j0 plus b times y0, and we know that y0 approaches negative infinity when r equals 0, and so therefore b is equal to 0. Okay. So BC2 implies that b is equal to 0. Okay. BC1 then implies this is that phi is equal to 0 at r equals 1. So what we have then is phi, which is on the left-hand side of this equation right here, is then equal to a times j0 of lambda. Okay. And so that implies that j0 of lambda is equal to 0, and I added an n here because there are infinitely many solutions to the equation, because lambda n are the, I don't know why I just did that, sorry, are the zeros of the Bessel function. Okay, if this looks a little unfamiliar, we actually did basically exactly this last time, because at this point in the previous solution, we said sine of lambda n is equal to 0. And then we said, well, when is sine of x equal to 0? It's when x is equal to 2 pi, or when x is equal to n pi, right? And we went around the unit circle, okay? And that's how we then figured out that lambda n is equal to n pi in that case. And that's why our basis functions were equal to square root of 2 sine of n pi y, right? Here, we don't have that luxury because, as I mentioned, we don't know what the zeros of the Bessel functions actually are, but that's okay. We can write them down, and you can look them up in a table. And you know what? When you get these solutions anyway, you have to plot them on a computer anyway, and so you just need to do one more step of looking those up instead of actually typing in n times pi. Okay, so lambda n are the zeros of J0.
Hey, Mitchell.
Yeah.
Is that lambda sub n or lambda times n?
Lambda sub n.
Okay, got it. Thank you.
Just like before, where we had lambda sub n is equal to n pi, it's basically there are certain values. These are called the eigenvalues again. There are certain values of lambda that actually solve this equation. Okay, and so what that then implies then is our basis functions look something like this. Remember, there are infinitely many basis functions, and each of them have an eigenvalue, the nth eigenvalue, the first, the second, the third, et cetera, et cetera. Okay. And just like before, we need to make sure our basis functions are orthogonal. And we talked about all the Sturm-Liouville stuff, and it turns out they actually are orthogonal, right? We showed that earlier. If you don't remember, go ahead and look at the recording earlier, or just scroll up in the notes. But we do need to normalize these basis functions, right? So basically, we need to find a sub n such that these are orthonormal. Or in other words, we need to normalize. Normalize. Okay, there we go. Okay, and so the way we do that is we do an inner product. And we make sure that the inner product of any basis function with itself is equal to 1. Okay, the inner product in this case looks a little different than normal. Because we have this additional r term right here. So the inner product is basically you take these two things and you multiply them together. But as we talked about in the Sturm-Liouville case, right, the inner product is defined as, sorry, I'm going to scroll. The inner product is defined now as multiply the two functions together, but now you have to multiply by this w function here. And in our case, the w function is not just equal to 1 as we had before, but in this case, the w function is actually equal to r. And so we have this additional r. This is kind of reminiscent a little bit of how in cylindrical and spherical coordinates, you have that little thingy at the end of all your integrals. There's always like an r or like an r squared sine theta or something like that, right? That's basically what this is. Okay, and just like before, we take, sorry, there should be a squared right here. Just like before, we have to take our two basis functions and multiply them together. Okay, and so now we need to evaluate this integral. We can do basically standard integral and then get something like this. I think you have to use integration by parts to get this integral. I don't expect you guys to actually figure out how this integral works. But the general indefinite integral in this case looks something like this. Okay. This you should be able to figure out using integration by parts and using properties like this up here. Okay. But this allows us to simplify. This term actually goes down to 0. because J0 of lambda n is equal to 0 because lambda n is equal to the zeros of the Bessel function. Okay, and so this then implies that the A sub n's look like this. Okay, and so therefore our basis functions look like this. And this is maybe not anywhere near as satisfying as what we've seen before with a square root of 2 sine of n pi y. But again, we were only able to do that because we're so familiar with circles and triangles and what sines and cosines are. In this case, we're dealing with basis functions, and so that's that basically. But again, you have something like sine of n pi y, except here we're dealing with we're dealing with a Bessel function right here. Lambda n you'd have to actually look up, and then J1 you'd also have to look up what the values of those are for lambda n, like that. Okay. So that's step one. Like I said, it's going to be a little bit more complicated to do step one, but again, we have to apply we basically express our solution as a sum of basis functions like this. Okay, and it turns out that our basis functions now look like this. Okay. There's also an inner product. I guess I should remind people. So our inner product is that, or the values of the coefficients in front of our basis functions are evaluated by the inner product of our original function and the basis functions. And that is defined by this. Okay, just like before, we also need to transform our PDE. That's our step 2. Okay, so we basically multiply the entire partial differential equation by our basis function and then do the integral. Okay, so we're going to do the inner product of this PDE, of every term in this PDE with phi n. Okay, just to remind you, the inner product in this case has an r term in there as well. Okay, as we wrote a little bit later. And so basically what we're going to do is multiply both sides of the equation by phi n times r, and then take an integral from 0 to 1. Okay, so the left-hand side looks like this. df/dt, not r, sorry. Okay. Here, just like before, you can pull the derivative out front. And when you pull the derivative out front, then this is essentially just the coefficients, just like before. Okay. On the right-hand side, we have 2 terms. So I'll say 1. To do that, actually, it's easier if we do 2. Whatever, let's just do 1. Okay. That first term on the right-hand side was just the value 1. And so we need to evaluate that inner product. That is the integral from 0 to 1 of phi n of r times r. And so we know what phi n of r is. That's this right here. So let me go ahead and plug that in. And so now it's just a matter of evaluating this integral. It's not anywhere near as intimidating as it looks. All these things over here are actually constants, and so I can just pull them out. That should be an n, my bad. Okay. And you can also evaluate this integral. You can basically use the properties of Bessel functions, right? You know that the derivative of this is equal to r j0 lambda r. And so then the integral of this is just equal to this. Okay. And so here I get same thing on the left or on the outside right here. And then this integral here becomes evaluate from 0 to 1, like that. Okay. And so if you go through the math and evaluate this, when r is equal to 0, then this whole thing just becomes 0, so that doesn't matter. When r is equal to 1, then whatever's inside here gives me 1 over lambda n times j1 of lambda n. That j1 of lambda n cancels with this j1 of lambda n, and so you get something fairly simple. It's just square root of 2 over lambda n. Okay. We have our second term. That second term looks like this. Where this L of r is that operator, 1 over r times d by dr. Here, I'll just write it out. This operator right here, this one is just 1 over r times d by dr, r df dr, like that, right? I'm just writing it shorthand. Okay. This is the integration by parts step. But again, the integration by parts here looks a little bit different. The result of that integration by parts looks like this. Okay. If you don't believe me, we talked about this a little bit on Friday. In general, in the Sturm-Liouville case, right, for a general operator, sorry, I'll scroll down just a second if you guys haven't copied that down yet, it's okay. In general, when I apply the integration by parts on an inner product like this, then I get this, okay, plus this bit right here. This term, because of the way that we constructed our basis functions, can reduce down to this. Again, this is where you take two derivatives and you end up with itself again, and so we end up with something like this. And then these terms just come out because we do integration by parts twice. In our case here, p of x is equal to r, and so that's where that r comes from. And then all this stuff in here is still the same. Okay. In our case, w of x is equal to r. Okay. And so this is basically what this all comes from. And as before, we can evaluate, here, let me make this a little more clear, from r equals 0 to r equals 1. We can evaluate this whole term at r equals 0 and r equals 1 using our boundary conditions of the basis function and the function itself and the PD itself, and show that all these terms actually go down to 0. Okay. And so this gives us negative lambda squared n of Fn of t. Okay. And so the PDE becomes an ODE that looks like this. Okay. Okay. We're almost there. Now we just need to transform our boundary condition. And so we'll get like an IC prime, which comes about because our original initial condition was that f is equal to 0 at a time t equals 0. And so now we get that Fn is equal to 0 at time t equals 0. And we can do that by just taking the inner product of f with our basis function, right? But because f is equal to 0, then therefore our individual coefficients are also equal to 0. Okay. And then the last bit, the last step, like I said, we're almost there, is we need to solve the ODE. Okay. So our ordinary differential equation was this, right? And then our initial condition is this. And so we just need to solve for f of n. Okay. To remind you guys, we talked about an equation that looks like this a little bit in the past. You have to use integrating factors, right? And so we get, let me go ahead and just draw, write everything in the standard form. Okay. You multiply both sides by something like e to the lambda n squared t. And so you can collapse the left-hand side like this. And then you end up with a general solution that looks like this. And to figure out what our integration constant C is, we apply our initial condition, right? And so our initial condition was that f is equal to 0 at time t equals 0. So when time t equals 0, then e to the negative lambda squared t is equal to 1. And so you just have a c right here. And so that implies then that c is equal to negative lambda squared, or negative square root of 2 lambda n to the third power. And so we get our overall solution for the OD looks like this. Yeah. Like that. And then therefore we can write everything then in terms of the basis functions. And so our overall solution looks like this. Yeah. And you can maybe see how this comes about. This is the basis functions right here, and then this is the coefficients of the basis functions that we figured out using our FFT solution. Okay, this looks kind of intimidating again, but again, you can just follow the steps, and then you should be able to find exactly what we need. In the homework, we'll ask you to do something similar to this, but using an alternative method of solving this problem. Okay. Also in the homework, we'll ask you to go maybe a few steps beyond this. For instance, here we have a velocity profile now, right? Now we can ask you, for instance, like what is the flow rate? You know, stuff like that. Okay. And so we might ask you for some of the problems a little bit beyond that. Just so that we can visualize things, let me go ahead and plot what this looks like. You guys are still seeing what I have here, right? I went ahead and wrote up some code that basically plots this. Let me see if there's a way of actually having the solution in front of us and showing you guys how to plot it. This is analogous to how we were doing it previously in the other plotting example, right? Again, we have a solution in terms of R and T, and then we need to sum over a few different values of N here, okay? And so just like before, okay, so I'm still using X, sorry about that, X, R, same thing, right? So I'm basically setting I'm setting a T max, and then I'm basically setting a grid of X and T values, or R and T values. That's what mesh grid here does, okay? I decided to basically only have 5 values of N in this case. And those values right here, these are the values of lambda N. Okay, that's exactly what, where's my cursor? I don't know why my cursor isn't showing up. Oh, okay, here we go. That's what these values of lambda N actually are, right? Like I keep mentioning before, we would have talked about those as things like N times lambda N is equal to N pi. So I didn't need to actually write those down. But here I just went online, I looked up what those values are. Okay. Express those again in terms of the third dimension, and so now my X and T are in dimensions 1 and 2, and then my third dimension is my N's, and I'm going to sum over the third dimension to get the to evaluate the sum. Okay, I pre-calculated a few of these to make my life a little bit easier, like this, and so then I basically typed in this, right? I have 2 in the front, lambda N to the third power on the bottom. Here's how you type in a Bessel function in MATLAB. It's just called Bessel J. You have to type in J1. So this is J1 right here, whereas this Bessel function right here is J0. Okay, and here's my N times R right here, and here's my lambda N squared times T right here. Okay, and then I sum, and then I get it. And so here's what I get. Sorry, it has a lot to plot, and so there it is right there. Okay, I'm gonna try and figure out how to rotate this guy so that we can actually see what's going on. All right, so physically what we might expect in our solution is that at time t equals 0, so along this line right here, you should have nothing moving, right? And then when time t goes all the way out to infinity, so maybe along this line over here, we should expect what our steady state velocity profile would be. What should our steady state velocity profile be? Does anyone off the top of their head? We've done pipe flow problems before, right? What does that velocity profile look like?
Is it a parabola?
It's a parabola, right? And so that kind of looks like parabola, right? And this value right here, this maximum value is 0.25. Okay. If you go back to when we non-dimensionalize the problem, remember we non-dimensionalize it in terms of u is equal to like, I have it in my notes here, is equal to gr squared over nu. You'll find that that actually corresponds exactly to what the pipe flow solution would be under gravity. Okay. So it's exactly a parabola like this. Now on this side, over here, you have r is equal to 1, so the no slip condition, right? And then basically what we're asking is how quickly does this flow profile eventually build and approach this steady state solution right here? Okay, and that's basically what we're seeing here, right? This over here does not look like parabola, right? It kind of looks like it almost exponentially approaches the correct solution right here to the finite, the limiting value at time t equals infinity. Okay, although we only went out to time t equals 1 because it stops being interesting after that point. Okay, but you know, we could just for fun make our t go out to like 5 or something like that. I actually haven't tried this before, but it should work out. Okay, cool. That's essentially what you see, right? After roughly t equals 1, it's essentially approached a steady state solution. And so this just looks like parabola all the way. Okay. And you could, for instance, calculate like how much is the flow rate before it reaches steady state, you know, stuff like that. Okay. Any questions at all about the solution?
Mitchell, I have a question on the velocity. So do we define u equal to g(r squared) over kinematic viscosity? Is that a condition or?
No, it just makes the math easier. We could have done this whole thing without any non-dimensionalization at all. It just makes it so that I don't have any prefactors and stuff in front of it, in front of any terms at all. If I had defined this u as equal to like, let's say 2 times g(r squared) over nu, then in my final solution, what I would have found is that the maximum value would not be 0.25. It might be something like 0.125 or 0.5. I can't remember which way it would be. Okay.
Yeah, but I thought u could be arbitrary.
Yeah, it could. This just makes everything look a lot easier to deal with, so that we don't have to carry through either order 1 prefactors or other terms like g or something like that. Basically, like in the actual equation here, then you then realize that like this one right here basically comes about because of the effect of gravity.
Okay, so it's kind of like a ruler or something.
Yeah. That's essentially what non-dimensionalization is. It's like our velocity scale in this case. The correct unit of velocity is g(r squared) over nu.
Okay, thanks.
Any questions at all with the basis with the Bessel functions and how we determine these basis functions and stuff like that? It's sort of the same thing over and over again. It's just a little bit of different variations of different things, right? You could imagine in the Cartesian, like in the rectangular coordinates case, for instance, where we kept getting basis functions that look like square root of 2 sine n pi y. That might not necessarily be the case either, right? Depending on different boundary conditions that you have and stuff. So in the example that I'll do during office hours on Wednesday, that might change a little bit as well, right? Although I'll mention that in Wednesday in lecture, we're going to start to talk about things that are beyond homework 2 and beyond exam 1 and stuff like that. Okay. All right. If there are no other questions, I'll see you guys on Wednesday.
Actually, Mitchell, I have one quick question.
Yeah.
So at the beginning, when we're non-dimensionalizing everything,
yes,
and we're going from dv over dt to uv over r squared. Oh, actually, never mind. I thought u was non-dimensionalized, but that's velocity. I was confused as to how that was the right units. Never mind.
Okay. Cool. All right, I'll see you guys on Wednesday.
Thanks.
All right, thank you.